F star. This is day 20. We'll get started in just a few minutes. Uh, so this afternoon I spent a little time working on one of the days I had missing. So I'm still missing both stars on day 17. Not so much because it's algorithmically difficult, but because I wanted to prove that the assumptions I was making were correct to F star. That's part of the benefit of using F star is it's a language where you can prove mathematical and computational facts about your program. And F star has really been giving me a hard time. I mean, let's be honest, doing basic algebra late at night is also hard. Um, but one of the things I managed to get through today was surprisingly difficult is this assertion here. So f stars works mainly in integers. I don't think there's a rational or real number class. I haven't used floats at all. Maybe I don't know if it has it. Anyway, so I was trying to prove that if n is odd, then we can rearrange the multiplication of n times n minus 1 over 2 to do the multiplication on the outside because n minus 1 divided by 2 is an integer, so it doesn't round down, and this equality is exact. And this is exactly the sort of thing that I think F star should be good at because it uses Z3 as a solver in the backend to judge the correctness of uh, mathematical of integer arithmetic like this. And I was a little surprised it could not. So I found something, an assertion that it could prove, and once it had proved this, it could just say, okay, yes, uh, I agree that your lemma is correct. And for the even case, it was a similar problem, right? I worked out on paper that if you know, if n is even instead, then when you move n to the outside the division, the difference is n divided by 2, because n minus 1 divided by 2 gets rounded down. So I was able to work through this by sort of putting in 2k's everywhere and simplifying. And so again, I kind of expected Z3 would be able to do something similar, and no, I had to tell it basically that that's what I did. Well, let k equals n divided by 2, so n equals 2k, and the second is just a placeholder because there's a lot of places 2k appears. And so I said, okay, well, is this true? And it said, okay, yeah, that's true, and then I can see how the lemma follows from that. But again, that just seems very difficult for something that's pretty basic computer mathematics. Like we're just dividing by an even number or an odd number by 2 here. So that was a little discouraging. So this is my day 17 solution in progress. I'm trying to prove what is the range that we need to search. In order to find a correct solution for the day 17 problem, we're going to have to search some range of possible velocities. And, we should prove that we're searching the right range. I saw a lot of solutions that just assumed it was no bigger than 1,000, and it worked, and there's nothing wrong with that. But if we can prove to F star that the solution really is in that range, then we'll have a lot more confidence that it's correct. So that's sort of an introduction to both the good and the bad of F star. One of the other things that's bad is F star does not have a very capable standard library. Um, It's sort of bare bones, and it's oriented around proving things rather than building things. So I'm going to set up the directory for today. Anyway, today is a fresh day. So the last couple days have been rough. They've been 3-hour slogs. But I did okay in the leaderboard on both of them. So I think we're getting to the part where sort of the clumsiness of me using F star isn't as big a factor. Or I'm getting better at F star, but it doesn't always feel like it. In fact, somebody else live streaming is Liz Fong Jones from Honeycomb, who is also a sponsor of Advent of Code this year, and she's doing it in Go. So almost every day she has finished long before I am done. But I was a little proud that I had managed to finish the same day and she had not. So that's probably the only time that will happen this Advent of Code. So my employer, Akita Software, is also a sponsor of Advent of Code this year. Akita Software builds API observability tools, and we're actively hiring. We're looking for a developer advocate, a front-end engineer, a product engineer, back-end engineers. We build in Go and Python, TypeScript on the front end, React. So I've done a little bit of everything in that stack. And I'm excited. It's a small team building something that I think is really exciting. To tell people things about how their API behaves that maybe they didn't know. To rebuild observability to operate at the API level rather than just looking at logs and traces and metrics. Because I've experienced this, other people have experienced this. It's always hard to get your code to the shape that you need it to be in to really use a current observability tool. There's always a lot of gaps. So we are good timing. About 5 seconds from getting started here. All right. Yikes. All right. The image enhancement algorithm describes how to enhance an image by simultaneously converting all pixels in the input image into an output image. Each pixel of the output image is determined by a 3x3 square. All right. So we can reuse the matrix I've built in earlier days. All right. So our okay. So we got a table lookup. It's okay. And we read them in row order. So top row, then second row, then third row. All right. All right, so we're given it's basically a cellular automata that doesn't have a boundary. So in part 2, we're only going to be asked to do the algorithm twice. And assuming it's an all reasonable, like 0 maps to 0, and we can check our input, then the pattern's only going to expand by a number of steps equal to the bounding box of our image is only going to expand by 1 each step. So today, for the part 1, we're only going to be asked doing it twice, but probably later we're going to be asked to do it many times. So the two options here are, instead of a matrix, we could keep a um, a map of which pixels are lit out of the whole infinite plane. And that would make sense if it's sparse. But this doesn't look sparse. So I think I'm going to go with the second option, which is just expand the matrix enough on all sides to accommodate the number of iterations we're going to run. So that should be fairly straightforward. And even if it's like 1,000, we should be able to handle that. And if it gets more than that, then maybe then we're probably not going to be able to do anything anyway if it's 1,000 dense pixels, but maybe that would change our priors on, how, this is a very dense matrix. I don't really want to represent that. So we're gonna cheat a little bit. We're gonna break up the input. So there's the whole input, and we're gonna break the rule out separately. But I think I'm actually just gonna include that in the source code. All right. All right. Well, okay. It's not a well-behaved rule. So 0 actually, the all 0 matrix actually neighborhood actually goes to 1 and then back again. This is going to change my mind about what's the best tactic to use. I'm not sure. We can certainly accommodate that with our original idea, but the problem is the border condition flips each time. So So this is a tricky thing that people who don't actually look at the input might miss. So I think that just means our border condition has to flip. We can simulate a bounded region exactly, and then just simulate the outside of that flipping every turn between uh, the hash and the period. So let's see if we can do that. And of course, the example that we were given doesn't do that. You know, its rule 0 starts with a dot. So we should probably I was going to say, can we guarantee that these are 512 bytes long? That has given me trouble with F star before. We can do it. We just have to do it in a weirder way. All right. Well, let's find our matrix parsing algorithm from a previous day. That was a matrix of natural numbers. Day 11 was the octopuses, octopi, whatever they are. Sure, let's use our day 15 code. Both of these have the wrong neighborhood. Huh. All right. Yeah, these are copied from a warm-up I'd done from the 2020 problem, but where there was the whole matrix. So all right. So we're not actually going to need an update, I think. Now we're going to need the neighborhood function. And this is where we're going to have to make a difference. Right. So instead of not oh no, this returns a list. Let me look at the 2020 solutions. Okay, there it is. Yes. So we're gonna, instead of returning a list of positions, we're just gonna have this return the list of values. So we're given a matrix, we're given two things inbound and a delta, and we're going to add to that a default value that's also of type A. All right, so let's make sure to assign these to build this up in the order we want. So we should start at -1, -1, assuming we have 0, 0 in the upper left-hand corner. We're going to go across and across and across. And since the function above puts things at the head of the list, we're going to list them in that same order. Okay, there's the first row. There's the middle row. And there's the bottom row. And we need to give it an empty list start and then just close all the way up. Oh, all right. Let's see, what do we need? Not sure yet. Default value, not A. Okay, good. Oh, all right. We need to give the default value here too. All right, so default value A, place M with M. Well, and this is a list A. All right, good. All right, so let's see. We're gonna need printf. We can just import list. That's fine for now. All right, so are we going to use characters? I don't really want to use characters. Let's use All right. Let's see, so we got our neighborhood. What else do we need to copy? All right, we need a bunch of boilerplate. All right, let's get our parsing function, copy that and adapt that. All right, to get the character type, we do need string. All right, so this, instead of a vector of natural numbers, it's going to return a vector of cells. So okay, so if it's a dot, then that's off. Oh. Come on. So all this is just to parse in the right order. I'm going to parse a row and verify the expected length, and the option type lets us either return some if the length matches, or none if it doesn't match, or we got a character we didn't expect. So let me just go through and change vector net to vector. Oops. Yep. Okay, we're missing another import. We're missing all. Okay, good. So there's our parsing function, and we also need this code that will let us iterate over the indices of the matrix. And I feel like this is overkill, but I didn't come up with a better way of doing it. Basically, this was what we want is um, to recreate a list between a start and end index. Everything's in the range. There are, in fact, in sequential order, which is stronger than the type I specified here, right? I just said everything's in the bounds, start to end, But really what we want is the sequential range, which is what it does. And we want to prove that it has the length equal to end minus start. So that's useful to say that if we use this to map over a matrix, then we get a matrix of the same size at the end. Which we could do differently, right? We could instead create a matrix of size 1 larger, 2 larger, in each index as we got larger. But be more efficient. I was thinking I was just going to copy the existing matrix into the middle. That would work best if we could start at -1 rather than 0, 0. And that would create some problems because we'd use nats throughout. So let's leave it be. All right, feed that all back in to the interactive session. All right, so we've got a parser. We need to write our transition function based on the rule. So for that, we're going to need to convert the number into binary, which we did on a previous day. Fortunately, bind is a very common name. Day 16. All right. So here's our function to do that recursively. So we're going to, instead of a list of bits, we're going to take a list of cells. So okay. So on and off. On is 1, 0 is off. All right. So the thing we need is to prove that that is less than 512. Okay, so let's prove that the length of this list is 512. Okay. All right. So what we're going to say is that the length we return here is specifically, okay, we need to give it a name to do this. So it's the list L. So the length L equals length old plus 1. All right, so we gave a more specific type the return value, and it verified, yes, in every case we do that, and so we should be able to say this is a list of length 9. All right, good. That was easier than I feared. We could do it all intrinsically in the function rather than prove it. So so what we'd like to show is if we get an input, then the length of n, then the result number is less than 512. Yeah, can only be 0 to 500. So that one I think we're going to have to do more work on. Okay. All right, so what we can do here is give another argument that's the bound. So I think we need to do this in the opposite order. So we're going to say the previous value is less than the bound. So n, if that is the case, then our result n has to be less than 2 times the bound. Is that a true fact? We may have to make a stronger guarantee for that to work. Okay. All right, this isn't working. So I was thinking we could start on with the bound of 2, but this function is recursive, so the bound we first give it is the one it's going to try to return. Okay, so we can still use that. So all right, so we take the remainder of the input. Let's make bound our first argument. Take a bound list of bits to continue reading the previous bound, which is a bound on previous, and we return something that's got everything. So what we need to say, yeah, this isn't so good. We don't use the power of 2 anywhere. I think we just have to, we need to switch from tail recursion. It's just calculating a bound. I mean, we could just check whether the result was big enough, but then it wouldn't be a total function anymore. It'd be harder to do proofs with it, and we could call it in fewer places. Should not be hard to prove that if our input is 9 bits, all right, let's just write the bound calculation. All right, let me. All right, so this is going to be sort of a hybrid function. This is going to be something that simultaneously calculates and proves the bound. So what this is going to say, we're going to return Okay. Nearly a month of this, I still can't get the syntax quite right on the first time for refinement types. The parenthesis and the curly brace keep wanting to switch places. All right. All right, so if you give it a 0 length input, then the bound is 1. Let's see if it agrees. Oops, I meant to just change the name of the variable. All right, it agrees. Yes, that's what bint in that aux does on an empty list. So what we need to do is say oops. Yeah, it can't prove that that's actually the case because our function. Okay, so we do need a previous bound. All right, so what we say is given a list and a previous bound, then calling the function with the input and the largest allowable value still returns a value less than or equal to bound. All right, let's see if our base case still works. Okay, this has to be this has to be greater than 0 in order to do the subtraction. Come on. All right, the base case doesn't work. This needs to be sharp. No, still wrong. All right, if we give it all right, if we call this function with an empty list and previous is 13, then the output should be 13, which is less than bound. Okay, so but it's not 1, it is the previous bound. Okay, good. So otherwise, we're going to call it with one smaller list. We're going to call it with all right, so our claim is if we just multiply the previous bound by 2, we get the new bound for the shorter list. Yeah, it didn't work. Okay, so this... Okay. So we got... We got something with this type. And we need to show that it is of this type. All right. So what I believe is I believe that those are equal, right? Because that's what the function does with the head. It either multiplies by 2 and add 1, okay, no, that's not quite true. It's either equal to okay, so it's either equal to 2 times this value or it's equal to 2 times this value plus 1. So let's spell that out. I'm just going to do put a helper value here so I'm not replacing. saying op multiply all the time. So the reason I'm using op multiply rather than something sensible like star is in F star, the star character is reserved for creating pair types. It's the Cartesian product times rather than the multiplication times. So there is a module you can import that will overload star to be multiplication. And the only time I've used it, I immediately said, "Oh crap, I need Cartesian product. Uh, I need ordered pairs to finish this solution." So I had to go back and change it. It's not ideal. If only our character had a time sign that was not star, then maybe something could be done there. It might be worth going back and like defining triple star to be op multiply or something like that, just to avoid so much typing. All right, so all right. So what I want to assert is okay. So this is going to be I'm losing track of it already. All right. All right. If we get this in, then its second argument is going to be that. I don't think we can reach in and get that. Oh, all right. Okay, so if we give it this bound, to get this. All right, what we're saying is this is less than or equal to So whichever case we get, if we give it this value, we either get this. I don't think this is right. Oh, just a type check. It should be simple. Let's rewrite our function to try to make it easier. But this was the easy way to write this function because that goes in the right order. Otherwise, we're going to have to know I'm going to have to know the next place digit. All right, let's do that. So this is going to return an n and the next. All right, so this will do both at once, sort of. So we're going to return a pair. Oh, is it a dependent type? All right, next place value and hello. Oh no. Everybody's here to witness my embarrassment that I can't even prove to F star how long a natural number is. How large a binary value can be. So I've copied a bunch of matrix code from previous days. Hello, welcome. So, yes, those alerts are very loud and scary, and I have no idea how to turn them down in Twitch Studio. I am still a Twitch Studio noob after a month. I went looking and I couldn't find them. All right. So what I want to prove is that if we take the neighborhood of size 9, that'll actually index a bit within a character within this string. And so what I'm trying to get to is just if we take an input of length 9 and convert it to binary using the function we wrote before, then it's bounded by 512. And this has been surprisingly difficult. So I had reverted to using a dependent type. So I'm changing my function that converts binary to natural numbers to tell us how long each number is. Yes, I am arguing with the type checker. F star is nothing but arguing with the type checker. So I was trying to rewrite this to say this is a natural number that is less than the next place value. So if we've got an input, if we've got an empty list, then our value is 0, and then our next place value is 1, and the only value it can be is 0. Okay. So otherwise, we're going to call the recursive value, and so we're going to get this smaller. So our next place value is twice the value we got back. So DFT is first for a dependent pair. And our real value is 2 times the actual value plus 1. All right, plus 1 and the dependent pair. And this is exactly the same, except it's just times 2. All right, so does that fly? Not if I don't close all the parentheses. All right, so we've got our binary to natural number parsing function to give us its own bound. All right, so the normal version is we just do d second on that. But I think we're still stuck here. I think we haven't actually... Oops, input. Oh, we don't need to do that anymore. All right, so still not proof. So we should be able to well, crap. All right, let's try something simpler. Let's prove that a length input of length 1, the bound is 2. So let's do it as a lemma. All right, so if you've got a length input, it's 1 length. All right, then what I claim, if I can spell length correctly, what I claim, what I want the type checker to verify is that the bound on Thank you. One of them actually mattered. The other did not. And I corrected the one that didn't matter. All right. I'm claiming that equals 2. All right. Do you agree, F star? I didn't actually make it. All right, let's try it non-recursively first. It does. All right. So can we just go all the way to 9? I don't think we can because it doesn't unfold that enough. No. So what if we ask the normalizer? All right. Why am I inventing the natural numbers again? Because the F star standard library doesn't have a binary to natural number. Okay. Ultimately, because I want this function with this type so that I can look up the neighborhood in the table. Because if I don't have this bound, then it's going to say, well, but you might have gone off the end of the array, which I could, just check every time, but then I'd have to throw an exception through God knows how many layers, or just fail the whole thing. So I think we only have to. I think we only have to reinvent the natural numbers up to 9 is the bad thing here. So all right. So we used our previous lemma. All right. This is so dumb. There's got to be a better way. The problem is F star doesn't have exponentiation, so I could invent the power of 2. All right. There's got to be a power 2 function somewhere. Okay. There we go. So, all right. So what we want to say is input length x. So we got x, a natural number, and input. So the bound on the value of that is equal to pow. Where? Oh, you gotta be shitting me. To do, maybe move this to f star int where people can actually find it. Okay, so not only does it have 2 to the x built in, it's automatically imported into every other module. It's in the primitives, and I don't know why. The other cute thing you'll notice while you're here is min is in the primitives, but maximum is not. There is actually no maximum in the F star standard library, as far as I can tell. All right. So this is pow2 of x. All right, and this we will need to show recursively. So if x equals 0, then hopefully it can get that case. Otherwise, x minus 1 and tail of the input. All right, so that, all right, good. So that does the thing I was going to do 9 times by hand. So we should just be able to say, use our lemma. So length x 9 input. Hurrah! All right, that was a lot of time to prove that the 9-bit integer is less than 512. So now we can write our transition function. So what days did we write a transition function with the octopuses? No, that was sort of funky, right? That was add 1 to everybody and then explode them. So I did the warm-up problem that had a transition function. All right, so we've got a list of cells, and we want to turn a new cell. And we've got this list rule that is a string. Why don't we parse the rule? So it's a list of cells of length 512. All right, and f star is currying, so we can just, so we should be able to pass the transition in function in elsewhere if we need it. And the cells are, the list is assumed to be the one we calculated up here, where we took the neighbors and we switched the default value of what we're using for everything outside of our matrix, because I don't know if Eric did this to everybody, but the example, translates the empty neighborhood to the empty neighborhood, and my input translates the empty neighborhood to all on. So you did it. Eric says he did it to everybody. Well, got to keep things interesting. All right. So it should be just 2 nat of, oh, gotta say this has length 9. Okay, and index rule. All right. So let's do our all right, so we got a map. So we're going to map our transition rule over the whole matrix. And I'm really hoping, so what I'm hoping is part 2 won't ask me to go out like a million iterations or something like that, because I'm just going to make the matrix big enough to take 2 generations for part 1. So I guess I'll find out. All right. So let's take our rule and our default value for whatever iteration this is, which is a cell. And we're going to return a matrix. Oops. All right, so we're mapping over the indices X and Y. I had some trouble getting this to work when I was warming up. It was very frustrating, but this works, so I'm not messing with it. So we're going to call transition on the neighborhood, and the neighborhood needs the default value. Default value, all right, and the transition function needs the rule. Hey, wow, all right. So for part one, we're just doing 2. I'm not going to count to 2. I'm just going to call the function twice and parse everything. So kind of like I did there. Oh, and then we're going to have to count all the live cells. Aha, very clever. We don't have to count to infinity. All right. I haven't written print matrix, and I haven't expanded the matrix into its new home. So let's do that. Okay, so we're gonna expand the matrix. So given, isn't that a movie coming out this year? Expand the matrix, return to the matrix, something. And this is going to return a matrix of cells of, let's give n, as long as we don't have to take the permanent of the matrix. All right, this is going to return a cell. All right. Just so we don't have to use that awful multiplication syntax. All right. This is not a smart thing. Let me, all right. New W equals new height equals height plus n. All right. New height, new width. That's not actually any shorter, but it is easier to make sure that I'm I know what I'm doing. Ha! All right, new width. All right, so instead of calling the transition rule, we're going to say if x is less than n. So if n is 1, 0 we're going to leave alone, 1 is going to be the old 0, 0. 1, 1 is going to be the old 0, 0. So if y less than n or x less than, x less than n, then off. Y greater than or equal to height, or y or x greater than equal to width, then off. Else we're going to get the regional value, so value at m y x. All right. Close the function. Set type check. Did we confuse the system so badly that we have to restart? Right. Now, periodically, the interactive environment just gets confused. It's supposed to remove things and add things as they're edited in Emacs, but you can watch how slowly it processes. It type checks all these stuff, retype checks all this stuff. All right, not happy. Computed type. I deleted row. There we go. Amazing. All right, so equals expand matrix. Yeah, 2. So which rule are we use? Oh, we didn't. All right, fooey. Let buried our parsing function. Oh, well, this should just work. It's a parsing function that says how long a row it expects. So rule equals list of string rule 512. Oh, does this return? Returns an option. All right. if all right, so we've got our rule. So the default value at time 1 matrix rule default value is off for anything off the border. No, we don't want the original board. We want the shifted version, and now the default value is on. Which isn't going to work to do the example. Okay. I will just okay. So what's the missing pieces here? Is it? I think it's print matrix. Yes. All right. All right. More copy and paste. Oh, needs to go in the opposite order. Have to define things, or at least specify their type before we can use them. There we go. Matrix cell. All right, good. All right, everything type checks. Let's try it out on the. That's our real input, and let's try it out on the example. Oh, and we need to give it the example rule. So this extracts all that F-star code to OCaml, and then compiles it as an OCaml file. And so it's reasonably efficient once compiled. Oh, and I forgot to put in a new line again. All right. Well, that doesn't look right. There's definitely a border problem there. There's all sorts of problems here. Oh. All right, let's oh, I know how to fix this. There's a function iter that just iterates and returns units. Even that first one doesn't look right. Oh. I'm confused. All right, that is definitely not it. Well, last year I actually tried to do Advent of Code in Pi, which is another dependently typed programming language, which is even worse because you really do have to invent things like addition every time. So F star is a step up where it at least knows addition. It doesn't necessarily know and multiplication. But yes, it's if you really want to be sure that you can say things about your code in a somewhat rigorous way, F star is one way to go about it. Yes, I know. All right, so it's probably my expand board function, but let's just make sure. That is very screwed up. Of course, since I didn't prove anything about the transition function, I only have myself to blame. All right. So things got shifted the wrong direction. Oh, I didn't shift them. That would help. Yes, so this should be y minus n and x minus n. I mean, we got other problems here. No, that's not right. That's not right at all. At least it's in the right place. Oh, all right. These bounds are wrong. Yeah, I should have drawn an ASCII art picture. We're shifting the window over we're extending it by 2n and shifting everything over by n. So, help if I save that. All right. So we shifted over by 2. Good. This is complete garbage. So I used example rule. All right. So all those 0, 0 should be 0. So default value. Oh, I changed both default. I've changed both default values to match. I changed them both to on rather than both to off. All right. There we go. Okay, not so good. Completely bogus. Not right at all. All right, so the most likely explanation is I messed up how we do the conversion. So let's. Star makes everything hard. What I want to do is create a matrix and use this function and make sure it matches the example in the program. So let example matrix equal, which is going to be a matrix of cell 3 by 3. And those are just lists of lists. So I hope this all works. Okay, so this is going to be starting at the top left and reading across each row. All right. Off, 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 off. On, off, off. Off, on, off. All right, and I guess our binary function was way down below, so. All right, so what we say is bind 9 to nat of neighborhood of example matrix. So that should be 34. Amusingly enough, Eric says it's a batteries included language. Many of FStar's data structures are based on the OCaml batteries included package, but they're all less capable. All right, so it says I couldn't prove that, but I actually kind of expected that. What we want is assert norm, which actually executes it in the normalizer. All right, let us print it out. Sure. Oh, neighborhood has to be, okay. Yeah, no wonder it couldn't prove it. It wasn't even well formed. Okay, matrix, default value off, not that it matters, and 1, 1. Okay. It should go faster. So one of the things I added to my make file is this record hints and use hints, which as it's proving things, dumps it out to a file. And then when it tries to prove it a second time, it can read it again in from that file. I got 136. Well, that's not right. All right. Y, X, dy, dx. All right. So the first element should be one, oh, 1, oh, 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 1, oh, oh. Okay, so exactly backwards. So the part I most likely screwed up was this one, the fancy thing I was writing when you all came in. Yes, that is completely backwards. So then we need to multiply our bit by the next place value. So it's all right. So on a 1 bit, we increment the place value, we add the current place value to whatever the rest of the string bits were, and here we just do nothing. All right, all right, does that still type check? Yes. Still obeying the bounds. I got 34. 34, all right. That looks right. And that looks right. All right, so let us count the number of pixels. And run the real example. All right, let count pixels. One pixel. Oh, we're counting like the count. 1 pixel, 2 pixel, 3 pixel. I don't have a lightning effect. What good is live streaming if I don't have a lightning effect? All right. So we're gonna do this as a fold, which ensures that I will screw it up. So we're gonna fold over count and the row and do something over M and 0. Is that the right order? No, it is 0 and then the row. Okay. So our function is going to take a count and a row and give us a new count. And so it's going to do that by folding over the row, starting with the count. Oops. Now, function first, then parameters. All right, something. One thing I miss is in Pi is you could put in a to do and it would tell you what type that was. Whereas here it'll just say, you know, I expect a different type. All right. So we start with the previous count and we do it on the row. All right, so here, if match cell, and if the cell is on, then we increase count by 1, and if it's off, we leave the count unchanged. All right. Does F star like that? It does not. But it is a list of cells. It's literally what it says. All right, I think I had to. Oh, I know. All right, what's it saying? So the problem is that a matrix is a list of cells, but the inner list is a refined type, and types in F star are not covariant. So if you've got a list of something special, it's not a list of the base type. And there's a function to do that, to fix that, which is list unref. No. What is it called? It's called list unref. Okay, so it looks like it's actually copying the list, but it's actually got when it extracts to ML, it just extracts the identity function. So it's not actually imposing an empty copy, an extra copy. Okay, so we need to do the same thing here. Oh, give me a break. I can't believe this is what's tripping me up. All right, when all else fails, be more specific in our types. All right, so this is going to be a row. The row is going to be a vector of length W of cell. No, well, that should be correct. Oh, it's a parentheses problem. Vector cell. All right. I don't know whether unref is actually necessary here, but it's harmless. Okay. Darn it. All right. Everything's still type check? Yes. They're running on the example for now. Should see 35. 50-50 will see 0 because I forgot to reset something using fold. Nope, that's 35. All right, all right, we can't run both at once. All right, so the default here is off and the default here is on for our new rule set. All right, looks plausible. Let's see how. It is a number. It's approximately the right order of magnitude. Hurrah! All right, now we have to do it 50 times. So let me just copy this. And we just have to write a and it's a natural number. Okay. Width, height. Let's give the matrix first. Matrix width of cell of width and height. And that return, we should handle the default value in a smarter way. But I'm not going to. I mean, we could pass in a flag that says, do we alternate or not? Sure. All right, and that returns a matrix of the same width and height. I thought about, could we just expand the border by one when we're doing the transition? Sort of combine, we could combine expand by one and then run, but this should be okay. It won't save us a lot. It would save us some. All right. So if n equals 0, then return the original. Else, what's our transition look like? Iterate n. So we transition the matrix. Okay, we need our rule, which is okay. And rule default value. All right. So the rule stays the same. Matrix transitions, n goes to -1, so so the problem with using a custom data type rather than something sensible like 0 and 1. Oops. I should have done all that. All right. Yeah, sample input is a little misleading. Okay, so if alternate, then opposite dv, else dv, and alternate doesn't change. All right, I think we got all the arguments there. Okay, we need to make the function recursive. Could not. Okay. So what it's complaining about is that we specified this as a total function, and all functions have to terminate. And it says, well, I don't know what you're doing. So we're just going to tell it we are decreasing n each time, and that guarantees we won't run forever. All right. So oh, no, we do want to expand this by 50. Yup. And then let m final equals iterate n rule m0 50 start with off, and for the test we will not iterate. We will not alternate. I mean, we could take alternate, or we could take alternation as well. I mean, or we could. I mean, if we're doing it right, we could derive it from the rule. It's look at the first character, but oh, yes, that's right. All right, let's try that out. Fancy. I'm a little worried we might have an off by one error lurking here, but let's see if our number is right. Yes, it is. Amazing. All right, so let's do input rule and do alternate. Yeah, the print's not as useful here, at least unless I make the text a lot smaller. I'm looking forward to people's GIFs of this on Twitter. All right, we did it. So in F star terms, what I'd really like is to be able to say some more about is the is not expand. Well, I mean, I'd like to say something about expand matrix because it was buggy. So that's a sure sign that I should have, written a proof it was correct. The thing I worry most about is like, what's our model for the transition matrix function? Could we describe its behavior with a lemma in anything short than re-implementing it? I'm not entirely sure how. And so that's why I'm still sort of very much a beginner in F star. It's like I don't know how to write this function in such a way that I can prove something about it, or even what I really want to prove. But we did manage to prove that the input had the right length, even though I screwed up the parsing and doing the neighborhood has had the right length. Basically what this function proves, this one, we at least know that the matrix is as much larger as we expected it to. The type checking verified that yes, the matrix was exactly as large as you said it was afterwards, but it doesn't verify anything about the contents. So yeah, let's look at the standings. I don't think this is going to be a new personal best. Yeah, it's a little easier than yesterday. Well, I picked up a little time. All right. The gifts are all seizure. Well, but to visualize it right, you should show every other frame, right? So it's not flashing at you. Well, if there are any questions about F-star, I'm happy to answer. Otherwise, I'm just going to call the stream to close, I think. And thanks again to all the organizers and sponsors of Advent of Code. I've been having a fun time this year. Like you said, I've got a couple at the start of the stream. I've got a few things I want to work back through. Mainly, it's just me being stubborn. I mean, those are real internet points. They're just evil internet points. Yeah, my best score rank was yesterday too. I spend a lot of time worrying about rotation, and I didn't get it right the first time. I had to go back and fix it. But once I did that, I had come up with what does the brute force algorithm look like, and I'd even written it down somewhere. It's like, well, let's loop over everything, and and I did that, and that was good enough. So I don't know if other people had an even harder problem with 3D rotation than I did, and it was pretty hard for me, even though I had my Rubik's cube to help me orient myself, or if it was just that they came up with ways that didn't work to do this nested looping. So, all right. Happy holidays. Happy Advent. And hope to see some of you tomorrow. I realize this is a rather specialized taste, though, watching me flail around trying to convince the type checker to work. So I appreciate you coming by. Good night. Thank you. I love the ASCII Aki too. I've been meaning to incorporate that in one of my outputs. I have it as an F-star module. I just haven't found a good place for it yet. Good night.